All right, so now I'm going to do a ride along for the acceleration test. Got the real-time data here. Got this terrible windshield, but it helps with the New Hampshire cold. Let's go. All right. This is really a need to get a throttle pedal here. Let's go. And oh yeah, you can feel the regen. It's hard to drive with one hand, but boy is it fun. So currently, power is limited to 200 amps peak, and regen current is set, I believe, to 20 total, because these batteries don't have very high charge current limits. But as you can see here, regen has a very appreciable amount of torque to stop you, at least sub 10 miles an hour and even above. Torque off the line is not great, but it's about what you'd expect out of a golf cart, if not even better. And speed, top speed, about 20 is how fast I've gotten it. Okay, so what I'd like to do now is give an overview of what has changed since my last video for the motor control setup and scheme. I'll show you guys the wiring changes, as well as then bring you in on the computer and show you the programming side, which is where most of the changes happen. So first thing is 2 batteries now, so we can deliver 200 amps max, 100 amps to each controller. Still have the same pre-charge setup as my last video. We'll be working on an automated pre-charge circuit for this car. But now we've got 2 of the G300 motor controllers. Each one is individually wired. One of them is the field and one of them is the rotor. This gives me individual control over the amount of current and the direction of current in each of those windings. What this has allowed me to do is set up a control scheme using a regular RC car controller. I'm only using the center stick. This is off right now, so I'm not going to do anything. But what I have is center is 0. Pull towards you like on an RC car. This is forward throttle. And then backwards is reverse throttle. What will happen is, if I give it reverse throttle, it's changing the direction of current that it should see in the rotor. Just like how the forward reverse contactor in the original Citicar changed the direction of current in the rotor to allow the motor to spin the other direction. If I push into reverse range while the car is moving forward, I will now have instituted regenerative braking. And as you'll see in the drive along video, it slows the car down. And on my real-time data, I also see the current going back through the motor into the battery. This is really cool for me because a lot of times DC motors in general and series DC motors are discussed as if they can't do regen, and you can only do regen on brushless DC motors and 3-phase type style motors, not these regular 2-wire motors. I guess technically this is 4-wire, but still. And that's not true. With this scheme, it is there and it's working great. Now, we'll jump into the software here and I will go over how it's all working. So in the motor controller settings, our control type is current. Now in VESC, there's current and current no reverse. current assumes reverse. What this means is, for the servo tester or for the RC controller, center is 0. Anything from 1500 to 2000 is positive current. Anything below that is negative current. This controller, the rotor controller, is set up quite simply. It does not have the script running to do anything fancy, because the rotor is the one we want to be changing the direction of current in. The rotor is the one that has brushes. That coil is meant to constantly have the direction of current change in. The field normally stays constantly in the same direction of current. So let me disconnect from this controller and let's connect to the field controller, which is where I have a Lisp script running that encapsulates most of my changes for this setup. So now we are reading the Field's G300 motor controller. What changes is the app settings. My app settings, we're now doing it set to PPM and UART because it is still getting a PPM signal in. However, in the PPM tab, control type is set to off. It is not doing any default control type. All the controlling is being done through Lisp scripting down here in the dev tools. And this is the Lisp script that I have running. Lisp uses reverse Polish notation, which I find very confusing to understand. But essentially, we come in, we define PPM and current, and we define a scalar number. This is the maximum current at max throttle to scale the PPM signal up into a current command. It's set at 222 just to get a nice full range with the RC controller, because that is not a perfect full range of motion. And what it translates to is my max current is about 95 amps. So essentially what's happening is we get the PPM signal, and then we're setting the PPM signal to be the absolute value of whatever it is. Because what we have coming in is a signal that goes positive and negative. And for the field, we want to send current in the same direction, whether we're going forwards or backwards. We only want to change the direction of the rotor. So with the rotor, we could just use the regular current setup because that control scheme switches direction. But for the field, we can't do that. So that's why we're doing this absolute value. We're adding in a deadband here. So when the stick is in the center and there's a little bit of fluctuation, there's not small amounts of current running through the motor. And then we're setting our current to be the PPM signal multiplied by the scalar. And that's pretty much all there is to it. And this just runs in an infinite while loop. Now, we'll go over to the whiteboard and I'm going to draw a couple graphs that hopefully make it easier to understand what I mean when I mention the absolute value and why I implemented this script instead of the current with no reverse control scheme I was using in the previous video. Okay, so what do I mean when I talk about reversing direction and doing an absolute value script for control rather than using the built-in control schemes of the VESC tool? Well, essentially, we can draw two graphs, one for the rotor and one for the field. Now, the rotor graph will look something like this. We'll have our axes, we will have current in amps on this axis, and this will be the PPM signal. Now, the PPM signal is centered around, let's call it 1500. The upper limit is 2000, and the lower limit is 1000. Those numbers don't really matter because you can tune them based on what the actual throw of your servo tester, or in my case, the radio controller is, but that's what we'll do. And then we have our max current of 200 amps and our max reversing current, which will also be 200 amps, because who doesn't want full speed in reverse? Now the control scheme we're doing is current with reverse, which is referred to in VESC tool as simply current, which looks like this. It's just a straight line. This is great because the rotor needs to reverse direction in just the rotor windings in order for the motor to spin the other direction. So that control scheme works out well. However, the field needs to not change direction, which means if we draw the field, this is what the field signal needs to look like. The astute among you will notice that this is just the absolute value of the rotor's current graph. And so this is at its heart why I am implementing a Lisp script. The Lisp script simply takes in the PPM signal right here, and by doing the absolute value, it will send positive current from 0 to 200 in the reversing direction as the current in the rotor ramps up, because it's really the magnitude of current going through, it's just in a different direction. So as this goes up, so does this. And then for going forwards, they just follow the same exact control scheme. So what's cool about this is that if you are driving forward and all of a sudden you tell the motor controller to be going in the reverse zone. So let's say you want to be here. However, you were driving and you were previously here. Thanks to physics and electromagnetics, the motor controller wants to suddenly switch the direction of current flow completely. But the motor is still spinning. And what the field wants the current in the windings to be doing is staying the same. So what will happen is the motor controller will actually draw current that is being generated in the windings because the motor does not want while it's moving, it wants the current to still be in this direction. And it'll do that, which will put current back into the battery. As you slowly fall down here, you're bleeding this current that the motor is generating now, in this case, into the battery as you slow down until you hit a stop. And then once you come to a stop, if you're still sending the signal, the motor controller will send current until you get there. And in this zone, you'll be going backwards.